All right, this is the final little addendum to what we were talking about. Free fall. Yes, when things are free falling, they're falling under the influence of gravity. And when something's falling, we said that the acceleration is negative 9.8 meters per second squared. Also, that would be negative 32 feet per second squared. All right? That acceleration is constant for our purposes, close enough to the Earth where we're dropping things or things are falling, people are jumping out of a plane, skydiving, and so forth. But there's a phenomenon of the air. So if you have, let's say you have a big bowling ball falling, or you have a piece of paper falling, and let's say I release them from some height. So let's say I'm up here, is 25 feet in the air. Well, what's going to happen is you're going to have air, because we breathe air and there's air molecules, and the air molecules are going to be hitting the paper and the bowling ball. So as they drop, because the bowling ball is more massive, you'll see the bowling ball actually hit the ground before the paper, because the paper is subject to air. So we have air. All right, so the ball will hit here, and then a couple of seconds later, this is going to float down. You've seen how paper falls. Now, that's in the presence of air. But in a vacuum, if you had no air, that would not happen. So if you had a bowling ball and a piece of paper in vacuum, so we have no air. No air at all. All right, and you did the same experiment from 25 feet, and you dropped them. What would happen would be the bowling ball and the paper would both hit the ground at the same time. So at the same time, they'd hit the ground. And that is because the acceleration due to gravity is constant and the same regardless of whether you're a bowling ball, a piece of paper, or anything else. It's independent of the mass. In air, yes, lighter type of things might have some air resistance, which will impede their accelerating at the same rate as a more massive object. However, in a vacuum, and that's important here, a feather will accelerate at the same rate as a bowling ball. So both a feather and a bowling ball will hit the ground at the same time in a vacuum. Which means that they are, if they're going to accelerate at the same rate and they're going to hit the ground at the same time, that means that they're going to have the same displacements at the same time. All right, so this will drop down the same displacement. This will drop down in the same time interval. So 5 seconds, this will be here. 5 seconds, this will be exactly lined up with it. So they're going at the same time. So the displacements will be equal on the way down. All right, I just wanted to clear that up. And there was one other last thing I wanted to say before we close this review. Wow, that looks pretty good. Okay, what I wanted to say was if you have a plot of, you have a plot of velocity versus time. All right, so you have some velocity versus time, and it's a straight line plot, right? So we're doing straight lines here. We're doing a line and maybe another. Well, okay, so it's like that. Maybe something like that, something straight, something down. Okay? Well, that's kind of sloppy, but I meant to have straight line segments here. You can have a straight line segment that's increasing. You can have a straight line segment here that's increasing. You can have a straight line segment that's horizontal, or one that's decreasing. All of those are physically possible. This means they're going at a constant velocity. right? Because this is velocity here versus time. Constant velocity means acceleration is 0. And remember what we said, acceleration is going to get, you're going to get the acceleration from slopes of these lines of a velocity versus time plot. So if the slope is horizontal, acceleration is 0. If the slope is like this, acceleration is negative. If the slope is like this, acceleration is positive. Now the only straight line that's physically impossible is a vertical line. Why? Because velocity, the time, it's going to have to take some time for velocity to change. So delta t cannot be 0 because acceleration is delta v over delta t. If you make delta t 0, this blows up to infinity. The equation's not going to make much sense. Okay? So as this gets really, really small, this gets really, really, really big. Physically impossible for there to be no time. You have to have some time in order to have a velocity change. So a vertical, all right, a vertical line on a velocity versus time plot is physically impossible. Okay, I guess that's about it.